This lesson will show how to use the central limit theorem to compute probabilities about sample proportions. Here's a situation. So to summarize, we have a certain car, and among the millions produced, 12% of them need mechanical repair within the first year. Now, if we were to choose a sample of 200 of these cars at random, is it possible that less than 8% of the sample would have a mechanical problem within the first year? Well, because samples vary, it is possible that something could be lower than 8%. So, to compute that probability, we need to look at the sampling distribution to see just how these samples are distributed. For this, we can make use of the central limit theorem for proportions. The central limit theorem tells us three things. First, that the sampling distribution will be normal, as you can see in the diagram. Second, that the mean of the sampling distribution will be the same as the population proportion with mechanical problems, in other words, the 12%. And the third thing that the central limit theorem gives us is a way to compute the standard deviation of the sampling distribution using this formula, where P is the population proportion, or the 12%, and 200 is the sample size. This all works out to be 0.023, or about 2%. In order to properly scale the diagram, we need to know where 8% lies in this distribution. Well, clearly it lies to the left of 12%, and I could make any mark to the left of 12% and call it 8%. But if I want my diagram to be reasonably to scale, I should look at this black dot, which is the steepest point on the curve, and remember that that is one standard deviation away from the center. In other words, the length of this green arrow is 0.023, or the standard deviation in our curve. Well, if that's the case, then wouldn't this tick mark be to the left of 12% by 2.3%? In other words, if I subtract 12% minus 2.3%, I get this number, roughly 10%. And if that black tick mark is at about 10%, then it's logical to estimate that 8% would be roughly here. Again, you don't need to have your diagram drawn exactly to scale to get the mathematically correct answer, but I personally like to do it that way. So now let's analyze the question shown in red. To ask whether, or the likelihood, that a sample proportion will be less than 8% is the same as asking what is the probability that that sample proportion were to land in this shaded region in my sampling distribution. In other words, I've converted this probability problem into a shaded area problem. And that's a good thing, because I know how to compute shaded area. To compute shaded area, we use our normal cumulative distribution function, or normal CDF. Now, most calculators, apps, and other software require a z-score in order to compute normal CDF. So I need to know the z-score corresponding to the 0.08 portion of my sampling distribution. So, calculating z-score, as we always do, that gives me the upper limit of my shaded area. The lower limit of my shaded area is technically negative infinity, because in theory anyways, this distribution goes on forever. So, substituting negative infinity and negative 1.74 into my normal cumulative distribution function using whatever calculator or software you use will give you 0.041. And that represents the red shaded area, but of course it also represents the probability we're looking for. The chance that out of 200 randomly selected cars, the sample proportion needing repair will be less than 8%. So there's a 4% chance roughly of that happening. Let's look at another example. Here's our situation. So in Missouri, 70% of the residents live in an urban setting. If we were to pick 120 residents from Missouri at random, how likely is it that our sample proportion, in other words, the proportion of our sample who lives in an urban setting, how likely is it that that proportion would be more than 5% away from expectation, meaning more than 5% away from 70%? Well, again, to analyze the probability of a sample proportion being in a certain location, we need the sampling distribution. Let's review the three things that the central limit theorem tells us about the sampling distribution. First of all, it tells us that the sampling distribution will be normal. Secondly, it tells us that the mean of that sampling distribution will be the same as the population proportion, in other words, the 70%. And third, the central limit theorem tells us how to compute the standard deviation of the sampling distribution. Again, using the same formula as before, and using p as 70%, we get the standard deviation for this particular sampling distribution. Well, let's analyze this phrase again, more than 5% away from 70. First of all, when they say expectation here, they mean 70%. We expect that 70% of our sample will be urban setting individuals from Missouri. Now, does that actually mean that every single time you take a sample that we would have 70% living in an urban setting? Absolutely not. But that's what they mean by expectation. But what does more than 5% away from 70 mean? What numbers are more than 5% away from 70%? Well, if you think about that, that's the same as saying that it's got to be below 65, because all of those numbers are more than 5% away from 70, or it's got to be above 75, because all of those numbers are again more than 5% away from 70. Well, this brings up the next question: where are 65 and 75 on my sampling distribution? Well, I could put them just about anywhere if I wasn't worried about scale, but I like things to scale. So I'm going to remind myself that this point here, that steepest point of your normal curve, is exactly one standard deviation away from the center. In other words, this distance, as indicated by this green arrow, is one standard deviation. Or in our case, that green arrow has a length of 0.042. That would mean that this point here is 4.2% higher than 70. In other words, 74.2%. But remember, I'm interested in where 75 is. Well, based on that black tick mark, 75 should be right about there, just to the right of that. By the same logic, 65% would be here. I want to remind you that the drawing of your diagram to scale will not ensure a correct mathematical answer, and you can get away with a non-scaled diagram, but again, I like that myself. It gives me a good sense of where everything actually is. But now back to the question. We want to know the probability that my random sample of 120 Missourians has a sample proportion of those living in an urban setting either below 65% or above 75%. And that's indicated by the two red shaded regions here. So what have I done? I've converted a probability problem into a shaded area problem. And I like that because shaded area is something I can calculate. To calculate shaded area, we're going to use normal CDF, but to use that function, we need z-scores for the boundaries of the shaded region. So here I've computed the z-scores. It should not surprise you by the symmetry of this problem that the two z-scores are opposite signs with the same number. In other words, one is positive 1.19 and one is negative 1.19. And using normal CDF to compute both of these areas, big surprise, tells me that both of these shaded areas are the same. Since I'm ultimately interested in the probability that my random sample proportion lies in either of these regions, I'm going to take those two numbers, add them together, and get a final answer of 23.4%. So in summary, there is a 23.4% chance that my sample average will be more than 5% away from what I would expect it to be, which is 70%. And that concludes the lesson.